Hey everyone, my name is Claude van der Merwe. I work on Beam, mostly on the Python SDK and trying to make machine learning use cases simpler. So today we'll be talking about introducing the concepts of embeddings, RAG, semantic search, and the role that vector databases play in this process, and how all this can be made possible with Apache Beam's RAG module. And then lastly, we'll have a demo to show what we've learned. All right, so I think a lot of you might be familiar with the limitations of traditional search. The most common limitation is that keyword matching misses semantic meaning. So for example, if you search for Apple stock price, traditional search might prioritize results about the apple fruit. In this way, traditional keyword search does not capture semantic meaning. You might think LLMs are the answer to these challenges, but they face additional problems. For example, let's say you ask an LLM to analyze Apple's latest stock report. An LLM might only be trained up to the end of 2024, and therefore it's highly likely that it'll hallucinate an answer. So RAG, vector search, and semantic models can help us address these challenges by combining retrieval with LLM generation. These can provide grounded responses with up-to-date information. So let's start with what are embeddings? At their core, they are a mathematical representation of meaning. Words are represented as dense vectors with hundreds of dimensions. And similar vectors are close together in the embedding space. We use mathematical distance as a measure of how similar concepts are. So that equals the semantic distance. These embedding models are trained on vast amounts of text to capture these relationships. Some of the commonly used embedding models are commercial models like Vertex AI, Gecko model. There are open source models available on Hugging Face sentence transformers, and some use cases might require fine-tuning models for specific domains, for example, financial data or code. All right, next, let's discuss some of the vector similarity measures that we can use to query embeddings. First off, we have Euclidean distance that measures the magnitude and direction. It's often used for k-means clustering. There's cosine similarity. It only measures the direction, the cosine of the angle between two vectors, often used for text similarity. And then there's dot product similarity, which measures magnitude and direction, but it's usually used for text similarity with normalized vectors. And a note on these, for normalized embeddings, all three of these measures will result in the same ranked semantic search results. Okay, next tool in the toolkit for semantic search is chunking. Okay, so why does chunking matter? Documents that we want to embed often exceed the token context limits of embedding models. This requires us to break a large document into smaller pieces that we can individually embed. Two common chunking strategies is the very simple fixed size chunking where, for example, every 20 characters, a document is chunked into a new chunk. And then you get more sophisticated ones that try to split documents on natural sentence barriers like new lines or paragraphs. Okay, So now that we understand embeddings and semantic search, we need a way to actually utilize these, and that's where vector databases come into play. So they're often specialized storage for embedding vectors, and they bridge the gap between the raw data and retrieval. Some of the common operations that vector databases offer are indexing. So it's a way of ingesting your vectors so that they can efficiently be looked up. Various search methods, for example, different search metrics like we just discussed, Euclidean distance, cosine, the ability to filter on additional metadata. So we might not just have an embedding stored, we might have more categorical data about what we want to filter on. And then the ability to update our embeddings. For example, in a streaming pipeline, we might want to keep our embeddings up to date as the data changes. So putting this all together, what is RAG, Retrieval Augmented Generation? It uses semantic search to enrich the LLM with external knowledge. And here's kind of a diagram for showing the architecture. So we have the ingestion piece, which takes documents from our document store, which could be streaming or batch. It chunks the documents into embeddable pieces. The embedding model creates vectors to capture the semantic meaning, and we store it in the vector database. Then we might have an application where a user prompts our application, and we might want to look up relevant information for their query that the LM wasn't trained on. So therefore, we embed their prompt, look up relevant information in a vector database, and provide the LLM with their prompt plus this additional context. Okay, so to make all this possible, we created an extensible RAG module in Apache Beam. The goal here is to make it as simple as possible to perform chunking, embedding, ingestion, and enrichment. And chunking currently supports the LangChain package. Embedding, we currently support local Hugging Face models, Vertex AI embedding models. Ingestion, currently supported is BigQuery and Postgres. And enrichment, also known as vector search, is we only support BigQuery. But if you feel there's anything you'd like to see here, feel free to implement your own vector databases, chunking strategies, or embedding models. Okay, so the first part of this RAG module is introducing the chunk class. So chunk represents a unit of embeddable content that we use through the embedding workflows. Okay, so as a chunk, you have the attribute content. This is what will be embedded. You have an ID for the chunk index. For example, if a document was divided into 3 chunks, the sequence of this chunk, any additional metadata, and then eventually the embedding for this chunk. So here's an example of what ingested data might look like. For a product catalog, you have a desk, you have its name, a description, and a category. And the ID might stay the same. The content you want to embed might be this description along with the name, and the metadata is the category. Okay, so now that we understand the chunk type, let's move on to how we actually perform chunking using the RAG module. So let's consider a pipeline where this is our input data. It's an unstructured dictionary. It has 2 sentences and some metadata. Okay, so to perform chunking, we import the ML transform, LangChain chunker, and the text split of the LangChain library that we want to use. next, we configure the LangChain chunker to split our text into 50 character chunks separated by periods. So this will try to keep natural sentence barriers. The field in our original input that we want to chunk on is content, and the fields we want to treat as metadata is the source and language. And we want to define a new function to create our chunk ID as the metadata source and the index. So if we run this piece of code, our input will be split into 2 chunks, the first sentence, the second sentence. And we have our IDs here, the index, and the metadata will be the same since they come from the same document. All right, next, we move on to the embeddings piece of the RAG module. Here, we take the chunks we left off with in the previous section, and now we want to add an embedding piece to it. So we import, in this example, the open source Hugging Face text embeddings handler. Again, we just change this to the ML transform. We specify the model name, and our output is our original chunks with the embedded content vector populated. Okay, so now that we have chunks with embeddings, how do we ingest it into our database? So for this part, we import our desired vector database configuration from the RAG ingestion module. We configure it with the table name we want to write to, some additional options. So create a table if it doesn't exist. If it exists, override it. A schema config, so how to convert our chunks into the rows that will be inserted into our BigQuery table. And as a result of running this, we write these chunks into the BigQuery table, and this is what it will look like. We have our content, embedding vector, ID, and metadata fields. All right, next up, now that we have our embeddings loaded into a database, we want to perform semantic search. So let's consider this scenario. We have an online store that contains a product catalog with embeddings. And we want a streaming pipeline that processes product queries and returns the relevant product. So here's what our BigQuery table might look like. We have the ID, embedding, description, and the price of our product. Okay, now let's consider our pipeline. The user's query might be they want a powerful laptop for video editing with a maximum price of $2,000. Okay, so how do we achieve a pipeline that performs this vector search and returns the right product? Okay, so to do this, we make use of enrichment transform. This is a powerful transform that joins external data sources to the data in our pipeline. And it combines with vector search through the RAG package where we need to specify the table we want to look up, the embedding column, the columns we want to retrieve, the metadata restriction template, and the number of results we want to return. So to put this pipeline together, we take our input, we convert it to a chunk so we can embed the user's query. We perform embedding, so the query is embedded and we have something to send to the vector database. And then finally, we do the enrichment piece where we provide these vector search parameters we specified, and we just want to return the top one closest result. And as a result, the user's chunk query contains the data from our vector database. It respects the maximum price restriction, and it returns the most relevant result. Okay, now we can move on to a Colab demo. All right, so here we will go through an example of how to embed the product data as we went through in the previous example. and then do an enrichment search for BigQuery. So let's consider this data source, the product catalog. And then let's define our BigQuery table. It's a table with an ID column, embedding column, content, name, category of the product, and all the other metadata we desire. Okay, so let's create this BigQuery table. Next, we define a function to turn our raw data into chunks. So what do we want to embed? We want to embed the product's name and the description, so that when a user searches, it matches their query to the closest product. Okay, so here we define the chunk creation function. Next, we configure our embedding model. Again, just a simple model from Hugging Face. And finally, we define the schema of our BigQuery table that we need to pass to the vector database writer, and how to turn our chunk into a format that represents our BigQuery table. So from the chunk, the ID column in our database is the chunk's ID. The embedding is just the embedding from our chunk. And the rest of the metadata fields just come from the metadata chunk property. Okay, so here we provide the BigQuery vector config that we just defined over here. We provide the table name we want to write to, the schema config, and then finally we run the pipeline to populate our database with the embeddings. This might take seconds, so let me move on to the previous run. So once that's done, the output will look something like this. We have a table. It's populated with our product data, the name, the category, price, and the embedding isn't printed here to save some space. All right, now let's move on to the enrichment part. Now let's say we have a streaming pipeline that continuously is receiving queries for products. Okay, so again, the user's query might be, I want a powerful laptop with a maximum price of 2,000, and then there's a couple more example queries. First step here is to create a pub subtopic, which is the source of our pipeline. It will publish the queries to our streaming pipeline. Here is just a function to parse the pub sub message into or to decode it into a dictionary and ultimately a chunk. As you can see, the content we want to embed is the user's query, and the metadata we want to extract from the user's query is the maximum price. We configure the Hugging Face embedding model. It's important to use the same embedding model for the user's query as used to populate the vector database. And then here we configure the vector search parameters. We have a table ID, the column in the table that contains the embedding, all the columns we want to retrieve, the number of neighbors, and the maximum price as a metadata filter. Okay, so here we just define a function to print the results we get back from our pipeline. So, okay, so here we run the pipeline, and when it runs for the first query, I need a powerful laptop for video editing with a max price of 2,000. Our vector search will return the product from our initial data that respects the price restriction and is semantically similar, a powerful ultra-light laptop, and so on. Here is another query for noise-canceling headphones. It retrieves from electronics headphones a very semantically relevant product. All right, so thank you all for listening to my talk.